The night sky has always made humans wonder. Since the earliest days when our ancestors looked up at the stars, we asked big questions. Where did everything come from? How long will it all last? And perhaps most haunting of all, how will it all end? This question about the end of the universe isn't just idle curiosity. It touches something deep inside us. When we gaze at the vast ocean of stars above, we feel small, yet connected to something enormous. The ending of all things matters to us in ways both practical and profound. Think about how different human cultures have imagined the end of everything. Ancient Norse myths told of Ragnarok, a final battle where gods would fall and the world would sink into the sea, only to be reborn anew. Hindu traditions speak of cosmic cycles where Shiva dances the universe into destruction before it begins again. Christians await the apocalypse and judgment day. These stories show how deeply we need to make sense of endings. But why should we care about an end that might happen trillions of years from now? None of us will be around to see it. The answer lies in what the question reveals about our present and our place in time. When astronomers and physicists study how the universe might end, they uncover fundamental truths about how reality works right now. The forces that will eventually determine the cosmos's fate are the same ones operating in our world today. By understanding the end, we better understand the present. There's also something uniquely humbling about thinking on cosmic timescales. Our human concerns, even the rise and fall of entire civilizations, occupy the tiniest sliver of cosmic time. Yet here we are, beings made of stardust, somehow able to comprehend the vastness that created us. When we contemplate the universe's mortality, we face our own in a new light. The journey from myth to science has transformed how we picture the universe's end. For most of human history, the ending of all things belonged to the realm of religion and philosophy. Gods or supernatural forces would bring about the final curtain. These weren't just stories. They helped people find meaning in a world full of smaller endings and beginnings. The scientific revolution changed everything, with telescopes, mathematics, and eventually sophisticated tools like space observatories. We began forming theories based on evidence rather than intuition alone. The universe revealed itself as far bigger, older, and stranger than our ancestors imagined. Today's cosmologists don't work with myths. They use general relativity, quantum mechanics, and observations of distant galaxies to create models of cosmic evolution. These models can be tested against real data. When we project these models forward in time, they give us possible scenarios for how everything might eventually end. What makes this question so powerful is how it connects to other deep mysteries. Time itself, that river we all feel flowing through our lives, changes meaning when we think about cosmic endings. Will time itself end? Will it continue forever in an empty universe? These questions force us to reconsider what time actually is. Space faces similar questions. Will it expand forever, stretching thinner and colder? Will it collapse back into a point? Will it tear itself apart? Each possible ending reflects something fundamental about the nature of space. And then there's meaning. Does a universe that ends still have purpose? If everything we build, discover and create will eventually be erased in cosmic death, what matters? This question has troubled philosophers since humans first realized the stars themselves aren't immortal. Scientists like Carl Sagan offered a powerful perspective. He once said, "We are a way for the cosmos to know itself." Perhaps our brief moment of awareness, our ability to wonder about endings, gives meaning regardless of how the story concludes. The question of the universe's end touches every field of human knowledge. Physics and astronomy provide the primary tools, but philosophy, theology, biology, and even art all have something to say about final things. Each approach offers a different window into this ultimate mystery. Even practical concerns connect to this distant question. How humanity should navigate the coming centuries, our relationship with our planet and each other, looks different when viewed through the lens of cosmic time. Our choices now represent precious moments in a universe that has existed for almost 14 billion years and might continue for trillions more. The amazing thing about modern cosmology is that we can now speak about the end with some precision. We have equations, observations and tested theories. While uncertainty remains, we're no longer simply telling stories. We're working with evidence that allows us to narrow down the possibilities. This evidence comes from many sources. The cosmic microwave background radiation, the oldest light in the universe, tells us about conditions shortly after the beginning. The motion of galaxies reveals how space itself behaves. The behavior of matter at quantum scales helps us understand fundamental forces. Together, these pieces help us project forward to possible ends. As we journey through this book, we'll explore how modern science has transformed ancient questions. We'll look at different ways the cosmic story might conclude. We'll consider what each ending would mean for the fundamental nature of reality. This isn't just about distant futures no human will ever witness. It's about understanding our moment in cosmic history. We exist in a specific chapter of an ongoing story. By learning how the story might end, we better understand our own place in its pages. Perhaps most importantly, we'll discover that the end of the universe isn't simply a scientific question. It's a human one. It touches our deepest fears and highest hopes. It challenges us to find meaning in impermanence. It invites us to appreciate the remarkable fact that we, collections of atoms with brief lives on a small planet, can contemplate the fate of everything that exists. The question of how the universe will end reminds us of something essential. We are not separate from the cosmos, we are part of it. Its story is our story, and by facing its eventual ending, we might find new ways to value the incredible gift of existing at all. Everything has a beginning. The universe is no exception. About 13.8 billion years ago, something remarkable happened. Everything we know, all matter, energy, space and time itself, emerged from a state of incredible density and heat. This moment marks what scientists call the Big Bang, but the Big Bang wasn't an explosion in space. It was an expansion of space itself. Imagine a tiny point containing everything that would become our universe. In an instant it began to grow. This growth continues today. The universe has never stopped expanding since that first moment. What existed before the Big Bang? This question might not even make sense. Time as we understand it began with the Big Bang. Asking what came before is like asking what's north of the North Pole. Still, some theories suggest possibilities. Perhaps other universes, endless cycles of expansion and contraction, or something beyond our current understanding. The earliest moments after the Big Bang were unlike anything we can easily imagine. The universe was incredibly hot, trillions of degrees. At these temperatures, even the fundamental forces of nature behaved differently. Everything was energy, too hot for even the simplest particles to form. As the universe expanded, it cooled. This cooling allowed the first particles to appear. First came quarks and electrons, tiny building blocks of matter. As cooling continued, quarks bound together to form protons and neutrons. These particles would eventually become the hearts of atoms. For about 380,000 years, the universe remained too hot and dense for atoms to form. Light couldn't travel far before hitting free electrons. The universe was like a fog, opaque and glowing. Scientists call this period the cosmic dark ages. Then something beautiful happened. The universe cooled enough for electrons to join with nuclei, forming the first atoms, mostly hydrogen with some helium. Suddenly light could travel freely. This light still exists today as cosmic microwave background radiation, the oldest light we can detect, carrying information from when the universe was very young. For millions of years after atoms formed, the universe was dark. No stars yet existed to light the cosmos. Gravity slowly pulled hydrogen and helium into denser regions. Eventually, these regions became dense enough for nuclear fusion to begin. The first stars were born, ending the cosmic dark ages. These first stars were giants, much larger than our sun. They burned hot and died quickly, creating heavier elements in their cores and in their explosive deaths. Each generation of stars created more complex elements. The iron in your blood, the calcium in your bones, the carbon in every living thing, all were forged inside stars that died long ago. As stars formed, they gathered into galaxies, vast collections of stars bound by gravity. Our own galaxy, the Milky Way, contains between 100 and 400 billion stars. But it's just one among trillions of galaxies in the observable universe. Galaxies themselves formed larger structures. They gathered into clusters, and clusters formed superclusters. These structures created what astronomers call the cosmic web, a pattern of galaxy filaments surrounding vast empty voids. This web represents the largest structures in the universe. About 4.6 billion years ago, in an ordinary spiral arm of the Milky Way, a cloud of gas and dust began to collapse. Most of this material formed our sun. The remaining dust and gas formed a disk around the young star. From this disk, planets formed, including Earth. The story of our cosmic origins had reached the chapter where our own story could begin. While all this was happening, the universe continued expanding. The rate of this expansion holds crucial clues about how everything will end. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He found that distant galaxies are moving away from us, and the farther they are, the faster they're receding. This observation led to a revolutionary understanding. The universe isn't static, it's growing. Every point in space is moving away from every other point, like dots on an inflating balloon. This expansion doesn't have a center. From any galaxy's perspective, all other galaxies appear to be moving away. For decades, scientists debated whether this expansion would continue forever or eventually reverse. The answer depends on the average density of the universe. If density is high enough, gravity might eventually overcome expansion, pulling everything back together in what scientists call the Big Crunch. The universe's beginnings set the stage for its eventual end. The amount of matter created in the Big Bang, the strength of fundamental forces, the properties of dark energy, all these factors established at the beginning will determine the final fate of everything. For most of the 20th century, most scientists believed the expansion would gradually slow down due to gravity. The question was whether there was enough mass to stop expansion completely and reverse it. Measurements suggested the universe existed in a delicate balance, with just enough matter to slow expansion, but not enough to reverse it. Then came a shocking discovery. In the late 1990s, two teams of astronomers were studying distant supernovas, exploding stars that shine with predictable brightness. These cosmic standard candles allowed precise measurement of cosmic expansion throughout history. What they found stunned the scientific world. The universe isn't just expanding, it's accelerating. Something is causing space itself to stretch faster and faster. This mysterious force, which scientists named dark energy, completely changed our understanding of cosmic destiny. This discovery represents one of the greatest plot twists in the story of cosmology. The universe we thought was gradually slowing down is actually speeding up. This acceleration points towards specific end scenarios and away from others. Our understanding of cosmic evolution has come a long way. Ancient people saw the heavens as fixed and eternal. The Greek philosopher Aristotle taught that the universe was unchanging, a series of perfect celestial spheres rotating around Earth. This view dominated Western thought for nearly 2,000 years. In the 16th century, Copernicus suggested that Earth orbits the Sun, not the other way around. This began a scientific revolution that transformed our understanding of the cosmos. Galileo's telescope revealed that the heavens weren't perfect and unchanging. Newton's laws explained the motion of celestial bodies. Each discovery pushed human understanding forward. In the early 20th century, Einstein's theory of general relativity provided a new framework for understanding space, time, and gravity. His equations suggested the universe couldn't be static. It must be either expanding or contracting. Einstein himself initially rejected this idea, adding a cosmological constant to his equations to create a stable universe. When Edwin Hubble discovered the universe was indeed expanding, Einstein called the cosmological constant his greatest blunder. Ironically, the accelerating expansion discovered decades later suggests something very similar to Einstein's cosmological constant might actually exist as dark energy. Another competing theory emerged in the mid-20th century. The steady-state theory proposed that the universe has always existed and always will exist in roughly the same form. As space expands, new matter is continuously created to maintain a constant density. This elegant idea avoided the need for a beginning or end to the universe. The discovery of cosmic microwave background radiation in 1964 dealt a fatal blow to the steady-state theory. This faint glow from all directions in space provides strong evidence for the Big Bang. It represents the cooled remnant of the universe's hot, dense beginning phase, exactly as the Big Bang theory predicted. Today's understanding of cosmic history rests on multiple lines of evidence. The expansion of the universe, the abundance of light elements like hydrogen and helium, the cosmic microwave background radiation, and the distribution of galaxies all support the Big Bang theory. As our knowledge has grown, so has our ability to project forward to the universe's end. The conditions established in the earliest moments after the Big Bang set cosmic evolution on specific paths. By understanding these conditions and the laws that govern them, scientists can make informed predictions about possible endings. The story of cosmic origins reminds us of something profound. Everything in our world, from stars to planets to living beings, emerged from the same beginning. We are made of stardust, born from the universe's ongoing evolution. Our existence represents a remarkable chapter in cosmic history, one where the universe developed the capacity to contemplate its own origins and ultimate fate. 4 invisible forces govern everything that happens in our universe. These forces are the underlying rules of reality. They determine how particles move, how stars shine, how galaxies form, and ultimately how the universe will end. Understanding these forces is essential to predicting the cosmic future. The first and most familiar force is gravity. We experience gravity every day as the force that keeps us on the ground and makes objects fall when dropped. But gravity does much more than that. It shapes the largest structures in the universe. Gravity is actually the weakest of the 4 fundamental forces. This might seem surprising since gravity feels strong to us, but compared to the other forces, gravity has very little strength. Pick up a paperclip with a small magnet and you're watching magnetism easily overcome the gravitational pull of the entire Earth. What makes gravity special is its range and cumulative effect. The other forces operate mainly at subatomic scales, or drop off quickly with distance. Gravity works across any distance and always adds up. Every bit of matter in the universe attracts every other bit of matter, no matter how far apart they are. This universal attraction gives gravity its cosmic importance. Over vast distances and enormous timescales, gravity pulls matter together. It formed the first stars from clouds of hydrogen. It gathered stars into galaxies and galaxies into clusters. On the grandest scale, gravity created the cosmic web of galaxy superclusters that forms the large-scale structure of our universe. Einstein's general relativity gave us a deeper understanding of gravity. It's not really a force at all, but a curvature of space and time. Matter tells space how to bend, and bent space tells matter how to move. This insight revolutionized our understanding of cosmic structure and evolution. For most of the universe's history, gravity has been in a cosmic tug-of-war with expansion. The Big Bang started everything moving apart. Gravity works to pull things back together. The balance between these opposing tendencies will help determine the ultimate fate of the cosmos. The second fundamental force is electromagnetism. This force governs electricity, magnetism and light. It's responsible for most of the phenomena we experience in daily life, from the light that lets us see to the chemical bonds that hold matter together. Electromagnetism is much stronger than gravity, but it comes with a limitation. It can both attract and repel. Opposite charges attract, like positive and negative, while similar charges repel each other. This means electromagnetic effects often cancel out over large scales. A typical object contains equal numbers of positive and negative charges, making it electrically neutral from a distance. Despite this limitation, electromagnetism shapes our world in countless ways. It creates the chemical bonds that form molecules. It drives chemical reactions. It allows atoms to emit and absorb light. Without electromagnetism, stars couldn't shine, chemistry wouldn't work, and life as we know it would be impossible. The third force takes us into the heart of the atom. The strong nuclear force holds atomic nuclei together. It's the strongest of all four forces, but only works at incredibly tiny distances, about the width of an atomic nucleus. Without the strong force, the universe would be unrecognizable. Protons are positively charged, so they naturally repel each other through electromagnetic force. In an atomic nucleus, multiple protons are packed tightly together. They should fly apart immediately due to electromagnetic repulsion. The strong force overcomes this repulsion, binding protons and neutrons together to form stable nuclei. This force powers the stars. In stellar cores, hydrogen nuclei are squeezed together with such intensity that the strong force can bind them, creating helium and releasing enormous energy. This process, called nuclear fusion, creates the light and heat that make stars shine. It also forged all the heavy elements in our bodies and our world. The fourth fundamental force is the weak nuclear force. Like the strong force, it operates only at subatomic distances. Despite its name, the weak force is actually much stronger than gravity, though weaker than the electromagnetic and strong forces. The weak force is responsible for certain types of radioactive decay. It allows neutrons to transform into protons, emitting electrons in the process. This transformation is essential for many nuclear processes, including those that occur in stars and in radioactive materials on Earth. While the weak force might seem less dramatic than the others, it plays a crucial role in stellar evolution and element formation. Without it, stars couldn't create the variety of elements needed for planets and life. The weak force helps determine when and how stars die, spreading heavy elements throughout the universe. These four forces weren't always distinct. In the extreme heat of the early universe, forces that appear separate today were unified. As the universe expanded and cooled, they separated into the four forces we now observe. Physicists have successfully developed theories that reunite electromagnetism and the weak force. They continue working toward a theory of everything that would explain all four forces within a single framework. Beyond these classic four forces, two mysterious components affect cosmic evolution in ways we're still trying to fully understand. These aren't forces in the traditional sense, yet they exert profound influence over the universe's behavior and its ultimate fate. Dark matter is the first of these cosmic mysteries. Unlike normal matter made of atoms, dark matter doesn't interact with light or electromagnetic force. We can't see it directly, but we can detect its gravitational effects. Galaxies rotate faster than they should based on their visible matter. Galaxy clusters behave as if they contain much more mass than we can see. These observations point to an invisible form of matter that outweighs normal matter by about 5 to 1. Scientists have proposed various candidates for what dark matter might be, from weakly interacting massive particles, WIMPs, to axions, to primordial black holes. Whatever it is, dark matter provides the gravitational scaffolding for cosmic structure. It formed the first gravitational wells where normal matter could collect, allowing galaxies to form. Without dark matter, the universe as we know it couldn't exist. Dark energy is even more mysterious. Discovered in the late 1990s through observations of distant supernovas, dark energy drives the accelerating expansion of the universe. Unlike normal energy and matter, which dilute as space expands, dark energy appears constant throughout space. As the universe grows, the amount of dark energy increases, accelerating expansion ever faster. We know very little about dark energy's true nature. It might be an inherent property of space itself, a cosmological constant similar to what Einstein once proposed. It could be a dynamic field that changes over time. It might even indicate that our understanding of gravity needs revision at cosmic scales. What we do know is that dark energy now dominates the cosmic energy budget. About 68% of the universe's energy matter content is dark energy, 27% is dark matter, and just 5% is normal matter. This distribution will determine how the universe evolves and ultimately ends. The laws of thermodynamics also play a crucial role in cosmic destiny. These laws describe how energy behaves, and they set fundamental limits on what's possible in our universe. The first law states that energy can neither be created nor destroyed, only transformed. The total amount of energy in the universe remains constant. This law helps us understand cosmic energy balance and how different forms of energy convert from one to another throughout cosmic history. The second law might be the most important for cosmic fate. It states that entropy, roughly speaking the amount of disorder, always increases in a closed system. Order can increase locally, as when life forms, but only by creating greater disorder elsewhere. This law gives time its arrow. It explains why eggs break but don't unbreak, why heat flows from hot to cold, and potentially why the universe will eventually reach a state of maximum disorder. Quantum mechanics adds another layer of complexity to our cosmic understanding. At the smallest scales, particles behave in ways that seem bizarre from our everyday perspective. They can exist in multiple states simultaneously until measured. They can tunnel through barriers. They can even pop into existence briefly from the quantum vacuum. These quantum effects might seem insignificant on cosmic scales, but they played a crucial role in the early universe and might determine its ultimate fate. Quantum fluctuations in the first fraction of a second after the Big Bang created the seeds of cosmic structure. Quantum effects might allow new universes to form from ours or trigger catastrophic changes in the fabric of reality itself. The interplay between general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the subatomic realm, remains one of physics' greatest unsolved problems. In extreme environments, like the heart of a black hole or the first moments of the Big Bang, both theories are needed, but they don't work well together. Scientists are searching for a theory of quantum gravity that would unify these frameworks. This quest for unification has led to fascinating possibilities like string theory, which suggests that the fundamental building blocks of reality are tiny vibrating strings of energy. Different vibration patterns create different particles. This theory requires extra dimensions beyond the three spatial dimensions we experience, curled up so tightly we can't perceive them. Whether string theory or another approach ultimately proves correct, the search for deeper understanding continues. Each advance in fundamental physics improves our ability to project the universe's evolution forward and narrow down the possible endings. The fundamental forces and laws described in this chapter aren't just abstract concepts. They're the basic rules governing everything from atoms to galaxies. The tension between gravity's pull and expansion's push, the gradual increase of entropy, the nature of dark energy, all these factors will determine how our cosmic story concludes. By understanding these forces, we gain insight into both cosmic history and destiny. The same laws that shape the universe's evolution from the Big Bang until now will guide its journey toward whatever end awaits. The key question becomes which force or principle will ultimately dominate cosmic evolution. The answer points toward specific scenarios for how everything might end. Our universe today exists in a special time. Stars shine brightly across space. Galaxies continue forming new stars from cosmic gas. Complex structures fill the cosmos from the smallest scales to the largest, but this rich, active universe won't last forever. To understand where we're headed, we need to understand where we are now. The observable universe extends about 93 billion light-years across. This might seem strange, since the universe is only 13.8 billion years old. Shouldn't we only see 13.8 billion light-years in any direction? The answer reveals something fundamental about cosmic expansion. Space itself has been stretching while light travels through it, allowing us to see much farther than we otherwise could. This observable universe contains roughly 2 trillion galaxies. Each galaxy holds billions or trillions of stars. Our own galaxy, the Milky Way, contains between 100 and 400 billion stars. Our Sun is just one average star in one spiral arm of this vast stellar city. But what really fills the universe? If we could somehow catalogue everything in the cosmos by its contribution to the total energy and matter, we'd find something surprising. The stuff we're familiar with, stars, planets, gas clouds, all things made of atoms, makes up just under 5% of the total. About 27% of the universe consists of dark matter. As discussed in the previous chapter, dark matter doesn't interact with light or normal matter except through gravity. We can't see it directly, but its gravitational effects are unmistakable. Without dark matter, galaxies would fly apart, and cosmic structures wouldn't have formed as they did. The remaining 68%, the largest portion by far, is dark energy. This mysterious force or property of space drives the accelerating expansion of the universe. Dark energy acts like anti-gravity, pushing everything apart on the largest scales. Its dominance today represents a relatively recent cosmic development, one that will shape everything that comes next. This distribution, 5% normal matter, 27% dark matter, and 68% dark energy, represents our best current understanding of cosmic composition. Future observations might refine these numbers, but the basic picture is clear. The universe is mostly things we can't see and don't fully understand. The most dramatic ongoing process in today's universe is its accelerating expansion. Every galaxy cluster is moving away from every other galaxy cluster, and this movement is speeding up. Nearby galaxies move away relatively slowly. More distant ones recede faster. At the edge of the observable universe, galaxies move away at nearly the speed of light. This expansion isn't like an explosion in space. The galaxies aren't moving through space. Space itself is stretching. Imagine dots on a balloon surface as the balloon inflates. The dots move apart not because they're travelling across the balloon's surface, but because the surface itself is expanding. We can measure this expansion using several methods. The most direct involves observing the redshift of distant galaxies. As galaxies move away, the light they emit gets stretched to longer, redder wavelengths. The greater the redshift, the faster the galaxy is receding. Another method uses cosmic standard candles, objects with known brightness. Type Ia supernovas are particularly useful. These stellar explosions release predictable amounts of energy, allowing astronomers to calculate their distance based on how bright they appear. By comparing distance with redshift, scientists can measure how the expansion rate has changed over time. In 1998, two research teams made a stunning discovery using this method. They expected to find that cosmic expansion was slowing down due to gravity. Instead, they found it speeding up. Something was counteracting gravity's pull, something we now call dark energy. This discovery fundamentally changed our understanding of cosmic destiny. While expansion dominates on the largest scales, gravity remains powerful within galaxy clusters and individual galaxies. Our Milky Way and neighbouring Andromeda Galaxy are actually moving toward each other. They'll likely collide in about 4.5 billion years, long before cosmic expansion would pull them apart. Today's universe is organised into a vast hierarchical structure. Individual stars gather into galaxies. Galaxies form clusters containing dozens to thousands of members. Clusters join into superclusters. These structures arrange themselves along filaments surrounding vast cosmic voids, creating what astronomers call the cosmic web. This web resembles a three-dimensional sponge or foam. Matter concentrates along the bubbles of this foam, with enormous empty regions between them. These voids aren't completely empty, they contain some galaxies, but they're much less dense than the filaments. The largest structures we can observe are these supercluster complexes and voids, extending hundreds of millions of light years. The Laniakea supercluster, which includes our Milky Way, spans more than 500 million light years. Beyond these scales, the universe becomes increasingly uniform, a principle called cosmic homogeneity. Our observations of the universe are limited by something called the cosmic horizon. Light travels at a finite speed, so we can only see as far as light has had time to travel since the Big Bang. Beyond this horizon lies more universe, potentially infinite, that we can never observe. Even within the observable universe, we see things as they were in the past, not as they are now. When we look at a galaxy 10 billion light years away, we see it as it was 10 billion years ago. The most distant objects visible are seen as they were shortly after the Big Bang. These ancient light sources show us how the universe has evolved over time. The most distant light we can detect is the cosmic microwave background radiation, the afterglow of the Big Bang itself. This faint energy pervades all of space, coming from all directions equally. It shows us what the universe looked like when it was just 380,000 years old. Hot, dense, and remarkably uniform, with tiny fluctuations that would eventually grow into today's cosmic structures. Modern astronomy relies on more than just visible light. Telescopes observe across the electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals different aspects of cosmic objects and processes. Radio telescopes show cold hydrogen gas. Infrared reveals dust-shrouded star formation. X-rays expose gas heated to millions of degrees around black holes and in galaxy clusters. Beyond electromagnetic radiation, we've recently gained new ways to observe the universe. In 2015, scientists detected gravitational waves for the first time. These ripples in space-time, predicted by Einstein's general relativity, are created by violent cosmic events like black hole collisions. They offer an entirely new window into the universe, allowing us to hear events we might not see. Neutrino detectors offer another novel approach. Neutrinos are nearly massless particles that rarely interact with normal matter. They stream from the sun, supernovas and other cosmic sources, carrying information from places light cannot escape. Their detection requires enormous underground tanks of pure water or other materials, monitored for the rare interactions between neutrinos and atoms. These diverse observational tools have revolutionized our understanding of the cosmos. They've confirmed the Big Bang theory, revealed the accelerating expansion, mapped dark matter's distribution, and shown us stars forming and dying across cosmic history. Despite these advances, major questions remain unanswered. The nature of dark matter continues to elude us. Multiple experiments search for dark matter particles, but none have made definitive detections. Dark energy presents an even greater mystery. Is it a constant property of space, or does it change over time? The answer has profound implications for cosmic fate. The origin of cosmic structure also poses ongoing questions. We know tiny quantum fluctuations in the early universe grew into today's galaxies and clusters, but details remain unclear. Why does the universe have exactly the structure we observe? Could it have developed differently? Scientists also continue working to reconcile general relativity with quantum mechanics. In most cosmic contexts, relativity adequately describes gravity's behavior. But in extreme environments like black hole interiors or the first instant after the Big Bang, we need a quantum theory of gravity that doesn't yet exist. Perhaps the most profound unresolved question is whether our observable universe represents all of reality. Inflationary theory, our best model of the universe's earliest moments, suggests our observable universe might be just one bubble in a much larger multiverse. Different regions might have different physical laws, constants, or dimensions. This possibility raises philosophical as well as scientific questions. If multiple universes exist, what does that mean for concepts like everything or creation? How should we think about cosmic endings if our universe is just one of many? These questions remind us of the limits of current knowledge. While we've made remarkable progress in understanding cosmic structure and evolution, we remain in the middle of the scientific journey. Each answer reveals new questions. Each discovery opens new horizons. What we do know with increasing precision is the universe's current state. We live in a cosmos dominated by dark energy, organized into vast filaments of galaxies and expanding at an accelerating rate. This knowledge, combined with our understanding of fundamental forces, allows us to make informed projections about possible cosmic futures. The universe today stands at a transition point in its history. For billions of years, matter dominated cosmic evolution. Gravity pulled things together, forming ever larger structures. Now, dark energy has taken over, driving accelerating expansion. This shift from a matter-dominated to an energy-dominated universe represents a fundamental turning point, one that points towards specific possible endings. When we think about how the universe might end, we're not just speculating. Scientists have developed detailed models based on our best understanding of physics. These models lead to several possible scenarios for the cosmic finale. Each ending follows logically from different assumptions about dark energy, cosmic density, and physical laws. The first and currently most likely possibility is called the heat death or Big Freeze. This scenario projects current trends forward to their logical conclusion. The universe continues expanding forever, accelerated by dark energy. Galaxies outside our local group eventually move beyond our cosmic horizon, disappearing from view. Stars burn out and aren't replaced by new ones. Gradually, all available energy becomes evenly distributed, a state physicists call maximum entropy. In this ending, the universe doesn't disappear. It simply becomes cold, dark, and empty. After countless trillions of years, only black holes remain. Even these eventually evaporate through a process called Hawking radiation. The final state would be an incredibly vast, cold space filled with nothing but extremely diluted elementary particles and radiation. This heat death derives from the second law of thermodynamics. Energy naturally flows from concentrated to dispersed states. Ice cubes melt in warm water until the temperature evens out. Stars burn until their fuel is exhausted. On the cosmic scale, this principle suggests a final state where no concentrated energy sources remain. No work can be done, nothing interesting can happen. Time itself becomes meaningless without change. The second possibility offers a very different ending. Called the Big Crunch, this scenario suggests expansion might eventually stop and reverse. If the universe contains enough matter, its combined gravity could overcome expansion, pulling everything back together. The universe would contract, growing hotter and denser, eventually collapsing into a state similar to the Big Bang. For decades, this scenario seemed plausible. Scientists measured cosmic density, trying to determine if it exceeded the critical density needed to reverse expansion. This critical value represents the dividing line between eternal expansion and eventual collapse. However, the discovery of accelerating expansion has made the Big Crunch seem unlikely. Dark energy pushes galaxies apart with increasing strength. For a Big Crunch to occur, dark energy would need to weaken significantly or transform into an attractive rather than repulsive force. Current observations show no signs of this happening. Still, some theories suggest dark energy might not remain constant. Its nature could change over cosmic timescales. If it weakened significantly or reversed its effects, a Big Crunch might still be possible. Some physicists find this scenario appealing because it mirrors the universe's beginning, creating a satisfying symmetry. The third possibility takes accelerating expansion to an extreme conclusion. Called the Big Rip, this scenario suggests dark energy might grow stronger over time. Eventually, its repulsive force would become so powerful it would overcome all other forces, even those holding matter together. In a Big Rip, the cosmic endgame unfolds with dramatic speed. First, galaxies are torn apart as dark energy overcomes gravity. Next, solar systems disintegrate. Then planets, people, molecules, atoms, and finally subatomic particles are ripped asunder. Space itself becomes fractured as everything is pulled infinitely apart. This scenario depends on specific properties of dark energy. If dark energy is a phantom energy that grows stronger as the universe expands, a Big Rip becomes possible. Current measurements haven't ruled this out, though they suggest dark energy's strength remains fairly constant over time. The timing of a Big Rip would depend on dark energy's exact nature. Some calculations suggest it could happen as soon as 20 billion years from now. Others project much longer time frames. In any case, the end would come suddenly on cosmic scales, with the final destruction unfolding over just minutes. A fourth possibility involves a phenomenon called vacuum decay. This scenario starts with the idea that our universe might exist in a false vacuum state, essentially a temporary energy configuration that appears stable but isn't truly at its lowest possible energy level. Quantum mechanics allows for random fluctuations. Eventually, somewhere in the cosmos, a small region might tunnel through to the true vacuum state with lower energy. This tiny bubble of true vacuum would expand at nearly the speed of light, transforming everything it touches. Inside this bubble, the laws of physics would be completely different. The fundamental forces, particle masses, and perhaps even the number of dimensions could change. Nothing as we know it could survive this transition. From our perspective, it would appear as a wall of destruction expanding outward, obliterating everything in its path. What makes vacuum decay particularly unsettling is that it could happen at any moment without warning. We would have no way to see it coming and no way to escape it. The wave of transformation would travel at nearly light speed, reaching us shortly after becoming visible. Scientists don't know if our universe actually exists in a false vacuum state. Some aspects of particle physics suggest it might, but the evidence remains inconclusive. If we do live in a false vacuum, the stability appears high enough that decay is unlikely to happen for trillions upon trillions of years, if ever. Beyond these four main scenarios, scientists have proposed several more exotic possibilities. Some involve cyclic universe models where each ending leads to a new beginning. Others suggest our universe might collide with a parallel universe or be consumed by a developing baby universe. These more speculative endings often connect to cutting-edge theories in physics, string theory, loop quantum gravity, or various multiverse models. While mathematically interesting, many lack clear observational evidence. They remind us how much remains unknown about the deepest laws of nature. The timeline for these various endings differs dramatically. Heat death would unfold over unimaginably long periods, quadrillions or quintillions of years. A big rip might happen in tens of billions of years. Vacuum decay could theoretically occur at any moment, though probability suggests the universe would last trillions of years before such an event. These vastly different timescales remind us that cosmic endings happen on timeframes almost beyond human comprehension. Our species has existed for about 300,000 years. Written history covers only about 5,000 years. The universe has already existed for 13.8 billion years and might continue for trillions more. So, which ending seems most likely based on current evidence? The heat death or big freeze currently has the strongest scientific support. Observations show dark energy behaving roughly as Einstein's cosmological constant, maintaining consistent strength over time. If this behavior continues, the universe will expand forever, gradually cooling to an eventual state of maximum entropy. The discovery of dark energy in 1998 fundamentally changed our understanding of cosmic destiny. Before this discovery, many cosmologists believed the universe's expansion would gradually slow due to gravity. The question was whether it would stop completely and reverse, leading to a big crunch, or simply approach a standstill. When astronomers Saul Perlmutter, Brian Schmidt and Adam Rees discovered the universe's expansion was accelerating, not slowing, it revolutionized cosmology. They earned the 2011 Nobel Prize in Physics for this discovery, which pointed towards very different cosmic endings than previously expected. Dark energy appears to be the deciding factor in the universe's fate. This mysterious force or property of space pushes everything apart on the largest scales. Unlike matter or radiation, which dilute as space expands, dark energy appears to maintain constant density. As the universe grows, the total amount of dark energy increases, accelerating expansion ever faster. The tension between gravity and expansion defines cosmic evolution. Gravity pulls matter together, creating stars, galaxies, and larger structures. Expansion pushes everything apart. For the first several billion years after the Big Bang, these forces were relatively balanced, with gravity dominating on smaller scales while expansion continued on the largest scales. Now dark energy has tipped this balance decisively toward expansion. While gravity still rules within galaxies and galaxy clusters, dark energy dominates the larger cosmic picture. The universe has entered an era of accelerating expansion that will shape everything that follows. This doesn't mean gravity has become irrelevant. Our Milky Way galaxy will still collide with the neighbouring Andromeda galaxy in about 4.5 billion years. The local group of galaxies will continue to merge into a single enormous galaxy over the next 100 billion years or so. Gravity still matters tremendously at these scales. But beyond our local group, every other galaxy cluster will eventually move beyond our cosmic horizon. No matter how powerful our telescopes become, we simply won't be able to see them anymore. They'll be receding faster than their light can travel toward us. The observable universe will grow increasingly empty from our perspective. The central problem facing cosmologists now is determining exactly what dark energy is and how it will behave over time. Is it truly constant, as Einstein's cosmological constant would suggest? Does it strengthen with time, potentially leading to a big rip? Might it somehow weaken or reverse, allowing gravity to reassert control? Current measurements support the constant model. Dark energy appears to have maintained the same strength for billions of years. If this continues, the heat death scenario becomes most likely, but our observations cover only a tiny fraction of cosmic history. Dark energy's behavior over trillions of years remains uncertain. This uncertainty reflects the nature of science itself. Scientific models represent our best current understanding based on available evidence. As new evidence emerges, models can change. The fact that we can narrow cosmic endings to a few possibilities represents remarkable progress in our understanding. Just a century ago, the idea that the universe had a beginning or would have an end remained controversial. Each potential ending reveals something profound about the nature of reality. The heat death points to the relentless march of entropy, the universe's tendency toward disorder. The Big Crunch suggests a possible symmetry between beginning and end. The Big Rip indicates dark energy's mysterious power. Vacuum decay reminds us how quantum mechanics introduces fundamental uncertainty into physical laws. These endings also raise philosophical questions. If the universe will eventually become uninhabitable, does that change how we should think about meaning and purpose? If all traces of everything ever accomplished will eventually disappear, what matters in the cosmic scheme? Some find these questions troubling, others find them liberating. The physicist Steven Weinberg once wrote, "The more the universe seems comprehensible, the more it also seems pointless." Yet others have found profound meaning in our brief moment of cosmic awareness. As Carl Sagan said, "We are a way for the cosmos to know itself." Perhaps the most remarkable aspect of this whole discussion is that we can have it at all. We are collections of atoms that have temporarily assembled into conscious beings capable of contemplating the fate of everything that exists. We've developed mathematics, physics and astronomy that allow us to project the universe's evolution billions or trillions of years into the future. This capacity for understanding represents something extraordinary, a universe that has developed the ability to study itself. Whatever ending awaits the cosmos, this chapter of conscious awareness gives the universe's story a unique significance. We get to ask these big questions, even if complete answers remain beyond our reach. As we look toward possible cosmic endings, we should remember that human knowledge continues to evolve. Future discoveries might reveal new possibilities or strengthen evidence for particular scenarios. The adventure of understanding continues, with each generation building on previous insights. For now, we can say with reasonable confidence that the universe appears headed towards eventual cooling and darkening. Stars will burn out. Black holes will evaporate. Usable energy will gradually dissipate. But this process will take place over timescales so vast they defy easy comprehension. The cosmos still has an enormously long story ahead. Imagine a cup of hot coffee sitting on your kitchen table. You know what happens if you leave it alone. The steaming liquid gradually cools until it reaches the same temperature as the room around it. This simple, everyday experience demonstrates one of the most powerful laws in all of physics, a law that may determine the ultimate fate of our universe. This principle is called the second law of thermodynamics. It states that in any closed system, entropy always increases over time. Entropy is often described as disorder or randomness, but it's more accurate to think of it as energy spreading out. Systems naturally evolve from concentrated energy states to more dispersed ones. The hot coffee contains energy concentrated in one place. Over time, that energy inevitably spreads out into the surrounding room. The second law explains countless everyday phenomena. Ice cubes melt in warm drinks, perfume molecules disperse throughout a room, hot things cool down and cold things warm up until everything reaches the same temperature. Life itself fights a constant battle against entropy, maintaining order locally by creating greater disorder elsewhere. Unlike many physical laws, the second law has a clear direction. It gives time its arrow. You never see a puddle of water spontaneously gather itself into an ice cube. You never see spilled perfume collecting back into its bottle. These processes would decrease entropy, violating the second law. Now let's think bigger, much bigger. The entire universe is also a closed system. No energy enters from outside and none leaves. According to the second law, the total entropy of the universe must always increase. This simple fact may determine everything about our cosmic future. When we apply the second law to the entire universe, we arrive at a sobering conclusion. Eventually, all the energy in the cosmos will spread out evenly. No concentrated energy sources will remain. Everything will reach the same temperature, a temperature just barely above absolute zero. Scientists call this final state maximum entropy or thermodynamic equilibrium. In this state, no more useful work can be done. Nothing interesting can happen. This endpoint is what physicists call the heat death or big freeze. Despite its name, the heat death doesn't mean things get hot, quite the opposite. The universe becomes incredibly cold as energy disperses to its thinnest possible state. This might sound like a depressing scenario, but understanding it requires us to think on truly vast timescales, far beyond human experience. The road to heat death unfolds over trillions upon trillions of years through distinct cosmic eras, each with its own character. We currently live in what astronomers call the stelliferous era, the age of stars. Stars illuminate our universe, powering life and creating the elements that form planets and eventually living beings. It's a vibrant cosmic epoch, but it won't last forever. Stars are temporary structures that fight against entropy. They concentrate enormous amounts of matter in small spaces, fusing hydrogen into helium and releasing energy in the process. But each star has a limited fuel supply. Eventually, every star will exhaust its nuclear fuel and die. Our sun has enough hydrogen to shine for about another 5 billion years. The smallest stars, red dwarfs, might burn for trillions of years. But even these long-lived stars will eventually consume all their fuel. The stelliferous era, our current cosmic epoch, will last somewhere between 100 trillion and 100 quadrillion years. That's an incredibly long time, but it's still finite. As stars die, some explode as supernovas, some collapse into black holes, and many simply cool into dense remnants called white dwarfs or neutron stars. New stars form from the gas clouds enriched by dying stars, but this recycling process isn't perfect. With each cycle, more matter gets locked away in objects that can no longer form stars. Eventually, the universe will exhaust its supply of star-forming gas. The last stars will be born, live out their long lives, and fade away. The once brilliant galaxies will darken. The cosmos will enter its next phase, the degenerate era. During the degenerate era, most visible light disappears from the universe. The primary objects are white dwarfs, dead stars about the size of Earth but containing the mass of our sun, neutron stars, even denser stellar corpses, and black holes. These objects contain significant energy, but they release it very slowly. White dwarfs gradually cool over trillions of years. Neutron stars slowly radiate away their rotational and thermal energy. Even in this darkened cosmos, interesting things occasionally happen. Sometimes degenerate stars collide, temporarily lighting up the darkness. Protons inside white dwarfs might decay very gradually, converting these dense objects into diffuse clouds. Brown dwarfs, objects too small to become proper stars, continue to glow dimly for trillions of years. The degenerate era lasts far longer than the stelliferous era. Somewhere around 10 circumflex 40 years. For perspective, that's 10 sextillion 0.00000000000000000 years. During this unimaginably long period, the universe grows increasingly quiet and dark. After the degenerate era comes the black hole era. By this time, most ordinary matter has either been captured by black holes or has decayed into light particles. Black holes become the dominant objects in the universe. These extreme objects, where gravity crushes matter into an infinitely dense point, seem like they might last forever. But even black holes aren't eternal. In 1974, physicist Stephen Hawking made a groundbreaking discovery. Using quantum theory, he showed that black holes aren't completely black. They emit a faint radiation, now called Hawking radiation. This happens because quantum effects near the black hole's boundary cause it to lose mass ever so slowly. For stellar mass black holes, this evaporation process takes an incredibly long time, around 10 circumflex 67 years. Larger black holes take even longer. The supermassive black hole at the centre of our galaxy might take 10 circumflex 100 years to completely evaporate. These timescales dwarf even the vast span of the degenerate era. As black holes evaporate, they release their stored energy back into the universe. Initially, this radiation is extremely cold, colder than the cosmic background radiation left over from the Big Bang. But as a black hole shrinks, its radiation grows hotter. In their final moments, evaporating black holes release enormous amounts of energy in a brief flash. These rare flashes briefly illuminate the otherwise dark cosmos. Eventually, even the largest black holes evaporate completely. The universe enters its final era, the dark era. By this point, around 10 circumflex 100 years from now, the universe consists almost entirely of photons, neutrinos, and other light particles. These particles continue moving farther apart as the universe expands. Matter as we know it has almost entirely disappeared. During the dark era, entropy approaches its maximum possible value. The universe reaches a state where everything has the same temperature, just barely above absolute zero. No significant temperature differences exist to drive energy flows or physical processes. The cosmos becomes quiet, dark, and essentially unchanging. Some physicists have speculated about exceedingly rare events that might occasionally break the silence of the dark era. Quantum fluctuations might rarely create new particles. Over vast spans of time that dwarf even the timescales we've discussed, random fluctuations might conceivably assemble more complex structures. But these events would be extraordinarily rare in an otherwise still universe. In this final state, time almost loses its meaning. With everything at the same temperature and no ordered structures remaining, the arrow of time fades away. The universe doesn't end in a dramatic flash or collapse, but in a quiet, cold whimper as entropy reaches its maximum. This heat-death scenario represents the most gradual and gentle of the possible cosmic endings. The universe doesn't disappear, it continues existing in an extremely diluted cold state. But nothing interesting can happen anymore. The cosmic story effectively ends, even though the cosmos itself persists. What evidence supports this rather bleak scenario? Several lines of observation and theory point toward heat death as our most likely cosmic fate. First, we observe the universe's expansion accelerating due to dark energy. This expansion works against gravity's tendency to pull matter together. Unless dark energy somehow weakens in the future, something we see no evidence for, the expansion will continue forever, spreading everything farther apart. Second, we've directly observed the second law of thermodynamics operating throughout the cosmos. Stars burn out. Galaxies gradually use up their gas for forming new stars. The cosmic microwave background radiation, the leftover heat from the Big Bang, has cooled from thousands of degrees to just 2.7 degrees above absolute zero. The universe clearly evolves from more ordered to less ordered states. Third, the general theory of relativity, our best description of gravity and cosmic structure, combined with observations of dark energy, strongly suggests an eternally expanding universe. This endless expansion naturally leads toward the heat death scenario as everything grows farther apart. Fourth, studies of the cosmos show its total entropy increasing over time, exactly as the second law predicts. Each star that burns out, each black hole that forms, each galaxy that exhausts its star-forming gas increases the universe's total entropy. We're observing the early stages of the very process that leads to heat death. The physicist Ludwig Boltzmann first proposed the heat-death concept in the 1870s, based purely on thermodynamic principles. Modern cosmology, with its discoveries about dark energy and accelerating expansion, has only strengthened the case for this scenario. Many cosmologists now consider heat death the most likely cosmic ending based on current evidence. The timescales involved in this scenario challenge human comprehension. The universe is currently about 13.8 billion years old. The Stelliferous era might last another 100 trillion years, about 7,000 times the current age of the universe. The degenerate era that follows lasts roughly 10 circumflex 40 years, about a trillion times longer than the Stelliferous era, and the black hole era lasts even longer. To put these timescales in perspective, imagine the entire 13.8 billion year history of our universe compressed into a single year. On that scale, human civilization would appear in just the last few seconds of December 31st. But the future Stelliferous era would last over 7,000 years. The degenerate era would continue for 10 circumflex 30 years, far longer than we can meaningfully comprehend. These vast time frames reveal something profound about our moment in cosmic history. We exist very early in the universe's story. We live in a young, energetic cosmos, still full of stars and galaxies. The universe we observe is in its bright, active youth, not its cold, dark, old age. Future generations of whatever life might exist will see a gradually darkening cosmos as stars burn out and aren't replaced. The heat-death scenario raises fascinating philosophical questions. If everything eventually reaches maximum entropy, does that mean the universe is ultimately pointless? Some have found this conclusion depressing. The physicist Steven Weinberg famously wrote, "The more the universe seems comprehensible, the more it also seems pointless." But others see wonder even in this scenario. The fact that the universe, though doomed to heat death, could produce beings capable of understanding their own origins and ultimate fate seems remarkable. As the astronomer Carl Sagan put it, we are a way for the cosmos to know itself. Perhaps meaning doesn't require permanence. A sunset isn't less beautiful because it fades to darkness. A piece of music isn't less moving because it ends in silence. Maybe our cosmic story has value precisely because it isn't eternal, because it represents a brief, remarkable period when energy gradients allowed complexity to emerge from simplicity, when the universe could think about itself through beings like us. The heat-death scenario reminds us that everything is temporary. Stars, planets, galaxies, and even black holes. But the laws of physics that govern this evolution appear timeless. The principles of thermodynamics that predict the universe's fate have operated consistently since the beginning and will continue operating until the end. This endpoint, this quiet, cold, dark fate, may seem strange and unfamiliar, but it follows naturally from processes we observe every day. The same principle that causes your coffee to cool on the kitchen table will eventually cause the entire cosmos to fade into darkness. The universe follows rules, and those rules have consequences that unfold across cosmic time. As we contemplate the heat death, we should remember that we're projecting current understanding forward over unimaginable time spans. Science continues to evolve. Future discoveries might reveal new factors that change our picture of cosmic destiny. But based on everything we currently know about physics, thermodynamics and cosmic evolution, the heat death represents our best understanding of the universe's ultimate fate. The journey toward this end will be gradual, so slow that if intelligent beings exist in the far future, they might barely notice the changes within their lifetimes. Stars will fade one by one. Galaxies will darken gradually. The cosmos will grow quieter and colder by such tiny increments that each generation might see it as essentially unchanging. Only across the vast sweep of cosmic time does the pattern become clear. This scenario might lack the drama of other cosmic endings we'll explore in subsequent chapters. There's no final collapse, no dramatic ripping apart of reality. But there's something profound in its inevitability, in the way it follows naturally from basic principles we can observe and test in our everyday world. The universe's end may be written in something as simple as a cooling cup of coffee. Imagine a ball thrown upward. It rises, slows, stops, and falls back down. This simple motion, governed by gravity, might parallel the universe's ultimate fate. In the Big Crunch scenario, cosmic expansion eventually stops and reverses. Everything that has been moving apart since the Big Bang begins moving back together, leading to a dramatic cosmic conclusion. This possibility offers a striking contrast to the heat death scenario. Rather than fading slowly into darkness, the universe would end in a fiery collapse, perhaps setting the stage for a new beginning. The Big Crunch represents a symmetric counterpart to the Big Bang, creating a poetic balance between cosmic birth and death. Gravity makes this scenario possible. We experience gravity as the force that holds us to Earth's surface and keeps planets orbiting the sun. But gravity operates on all scales, from apples falling from trees to galaxies pulling on one another. Every piece of matter in the universe attracts every other piece, no matter how far apart they are. This universal attraction creates a cosmic tug-of-war. The Big Bang started everything moving outward. Gravity works constantly to slow this expansion. If gravity wins this contest, expansion will eventually stop. The universe would reach a maximum size, pause, and begin contracting. During contraction, galaxies would start moving toward rather than away from each other. Initially, this movement would be gradual, but like a ball falling faster as it approaches the ground, cosmic contraction would accelerate. Galaxies would crowd closer together. The universe would grow hotter and denser. In the final stages, conditions would mirror the early universe in reverse. Galaxies would merge, stars would collide. As space itself contracted, temperatures would soar to incredible levels. Atoms would break apart into their components. Eventually, all matter would compress into an extremely hot, dense state, similar to the conditions just after the Big Bang. What happens at the very end of this collapse remains speculative. Some theories suggest the universe would reach a singularity, a point of infinite density where our current physics breaks down. Others propose that quantum effects would prevent a complete collapse, leading instead to a big bounce that initiates a new phase of expansion. For the Big Crunch to occur, specific conditions must be met. The most important factor is the average density of the universe. If this density exceeds a critical value, gravity will eventually overcome expansion. If density falls below this threshold, expansion continues forever. Scientists express this relationship using the concept of omega, O, the ratio of the universe's actual density to the critical density needed for eventual collapse. If omega exceeds 1, the universe is closed and will eventually experience a big crunch. If omega is less than 1, the universe is open and will expand forever. If omega equals exactly 1, the universe is flat, and expansion will gradually slow but never quite stop. For decades, determining omega's value was a central goal of observational cosmology. The answer would reveal the universe's ultimate fate. Early measurements suggested omega might be close to 1, keeping the Big Crunch possibility alive. However, sophisticated observations in recent decades have dramatically changed the picture. Studies of distant supernovas, the cosmic microwave background radiation, and galaxy distribution all indicate that the universe's expansion isn't slowing down, it's speeding up. This acceleration points away from the Big Crunch scenario. The cause of this acceleration appears to be dark energy, a mysterious force or property of space that acts against gravity on cosmic scales. Unlike normal matter and energy, which become more diluted as space expands, Dark energy appears to maintain constant strength regardless of expansion. As the universe grows larger, dark energy's influence grows stronger relative to gravity. Current measurements suggest our universe has omega approximately equal to 1, making it essentially flat. But this flatness doesn't mean expansion will gradually coast to a stop. Dark energy pushes toward ever faster expansion, making a big crunch seem increasingly unlikely based on current evidence. For a big crunch to occur, given what we now know, dark energy would need to change its behavior dramatically. It would need to weaken substantially or somehow transform from a repulsive to an attractive force. Current observations show no signs of such changes, though they remain theoretically possible. Some theorists find the Big Crunch appealing despite observational challenges. It creates a symmetry between beginning and end that some find intellectually satisfying. It also potentially solves the problem of cosmic finity. If the universe both begins and ends in similar states, perhaps this cycle has repeated endlessly, removing the need for an absolute beginning or end. This idea leads naturally to cyclic universe models. In these scenarios, the Big Crunch isn't truly an end, but a transition to a new beginning. The collapsing universe compresses to an extremely dense state, then rebounds in a new Big Bang. Each cycle of expansion and contraction represents one bounce in an eternal series. Cyclic models have appeared in various forms throughout scientific history. In the 1930s, physicist Richard Tolman proposed an oscillating universe model where each cycle would be slightly longer than the previous one due to entropy increases. More recent versions include Paul Steinhardt and Neil Turok's ekpyrotic universe model, which involves interactions between our three-dimensional world and extra dimensions proposed by string theory. These models face several theoretical challenges. The most significant involves entropy. If entropy always increases according to the second law of thermodynamics, each cosmic cycle should have higher entropy than the last. Eventually, entropy would reach maximum, preventing further cycles. Some theories attempt to address this issue by proposing mechanisms that reset entropy during the bounce phase, though these remain speculative. Another challenge involves the physics of the bounce itself. Classical general relativity predicts that a collapsing universe would reach a singularity of infinite density, where physics breaks down. For cyclic models to work, some mechanism must prevent this complete collapse and trigger the next expansion. Quantum gravity theories, attempts to combine quantum mechanics with general relativity, might provide such mechanisms, but these theories remain incomplete. Observational evidence for cyclic models is difficult to obtain. Since each cycle erases most traces of previous cycles, we can only directly observe our current cosmic epoch. However, some cyclic models predict subtle patterns in the cosmic microwave background radiation or gravitational wave signatures that might eventually be detectable. The concept of cycling universes connects to broader multiverse theories. Rather than a single universe repeatedly expanding and contracting, some models propose vast numbers of universes existing simultaneously. These parallel universes might form through various mechanisms, creating a much larger reality beyond our observable cosmos. One such mechanism involves eternal inflation. The idea that the rapid expansion that occurred just after the Big Bang continues indefinitely in some regions of space while stopping in others. This process creates bubble universes that form and expand within an ever-inflating background. Our observable universe would be just one bubble in this much larger structure. Another multiverse concept comes from quantum mechanics. In the many worlds interpretation, each possible outcome of a quantum event occurs in a separate branch of reality, creating countless parallel universes that continuously split from each other. While mind-bending, this interpretation follows mathematically from core quantum principles. String theory, an attempt to unify physics at its most fundamental level, suggests yet another multiverse possibility. Different configurations of extra-spatial dimensions could create universes with different physical laws and constants. Our universe might be just one of a vast landscape of possible universes. These multiverse concepts expand our thinking beyond simple birth-life-death models for a single universe. Perhaps our cosmos is part of something much larger and more complex. Something with many beginnings and endings happening across a reality broader than we can directly observe. Testing multiverse theories presents enormous challenges. By definition, other universes exist outside our observable reality. However, these theories sometimes predict subtle effects that might be detectable in our universe. For instance, our universe might have collided with another in the distant past, leaving faint bruises in the cosmic microwave background radiation. Scientific investigation of cyclic and multiverse models represents cosmology at its most speculative edge. These ideas push against the boundaries of what we can observe and test. Yet they follow logically from established theories and observations, showing how science continuously expands its conceptual horizons. The observational hurdles facing the Big Crunch scenario and cyclic models are substantial. Current evidence strongly suggests dark energy will continue driving accelerating expansion, making a future collapse seem unlikely. Any theory proposing eventual contraction must explain why dark energy would change its behavior radically from what we currently observe. Modern precision cosmology has transformed our understanding of cosmic destiny. Decades ago, the universe's fate seemed balanced on a knife edge, with eternal expansion and eventual collapse both plausible. Now, evidence strongly favors continued expansion. The balance has shifted decisively against the Big Crunch scenario. This shift exemplifies how science works, through observation, measurement and revision of theories based on evidence. The Big Crunch remains mathematically possible and philosophically interesting, but observational support has weakened significantly. Science follows evidence rather than aesthetic preferences or philosophical appeal. However, science also reminds us of the limits of current knowledge. Dark energy remains poorly understood. Its nature and behavior over cosmic timescales involve substantial uncertainty. Future observations might reveal aspects of dark energy that would change our projections for cosmic evolution. The expanding space telescopes, gravitational wave observatories, and sophisticated computer models continuously improve our understanding of cosmic evolution. Each advance helps narrow the range of possibilities for how the universe might end. While the heat death scenario currently has stronger evidential support, we should maintain appropriate scientific humility about predictions spanning trillions of years. The Big Crunch scenario, despite its observational challenges, serves an important role in cosmological thinking. It reminds us that gravity, the most familiar of fundamental forces, remains a key player in cosmic evolution. It highlights the dynamic balance between expansion and gravitational attraction that has shaped the universe since its beginning. The concept also connects to deep human intuitions about cycles and renewal. Many ancient cultures envisioned cosmic cycles rather than linear time. The Hindu concept of cosmic ages, yugas, creating larger cycles, kalpas, the Aztec sun cycles, Norse Ragnarok followed by rebirth, these mythic patterns reflect human recognition of natural cycles and desire for renewal after ending. Modern cyclic cosmology transforms these ancient intuitions into precise mathematical models based on physics rather than mythology. While evidence currently points away from these models, they remain part of the scientific conversation, examples of how cosmology continues exploring all logical possibilities consistent with fundamental physics. Perhaps most importantly, the Big Crunch and cyclic models illustrate the remarkable flexibility of cosmic possibilities. Small changes in fundamental parameters or forces could create radically different cosmic futures. Our universe might have easily been one that eventually collapses rather than expands forever. This sensitivity highlights how finely balanced cosmic evolution appears to be. As we consider these alternative cosmic destinies, we should appreciate the extraordinary progress in our understanding. A century ago, we didn't know the universe was expanding. We didn't know about dark energy. We had no way to measure cosmic density precisely. Today, we can meaningfully discuss and test different scenarios for how everything might end trillions of years in the future. This progress represents one of humanity's greatest intellectual achievements, the ability to comprehend cosmic processes spanning billions of years and billions of light years. Whether the universe eventually crunches back together or fades into darkness, our ability to understand these possibilities reveals something profound about consciousness itself. The debate between eternal expansion and eventual collapse connects to fundamental questions about time, space, and existence. Is time infinite or finite? Does physical reality have a beginning and end, or does it continue eternally in some form? These questions stretch beyond science into philosophy, showing how cosmology touches our deepest wonderings about reality itself. Even if the Big Crunch proves unlikely for our universe, the concept enriches our cosmic understanding. It reminds us that expansion and contraction, birth and death, represent fundamental patterns throughout nature. From heartbeats to breathing, to planetary orbits, to market cycles, oscillation between opposing forces creates the rhythms of existence across all scales. Our cosmic story, whether ending in fire or ice, touches something essential about how we understand ourselves. We are beings who can contemplate beginnings and endings, who can project our minds across timescales far beyond individual human lives. This capacity for cosmic perspective represents something remarkable about consciousness itself. The possible futures we've explored in these chapters, heat death's gradual cooling or Big Crunch's dramatic collapse, represent opposite endpoints on the spectrum of cosmic possibilities. Each tells us something important about fundamental forces and principles operating in our universe. Together they help us understand the cosmic drama that has been unfolding since the Big Bang and will continue long after all humans are gone. The universe might end in several ways. Two of the most fascinating possible endings are the Big Rip and vacuum decay. These ideas come from our understanding of physics and what we know about the universe. Dark energy fills our universe. We cannot see it or touch it, but it pushes everything apart. Most things in space pull other things closer because of gravity, but dark energy does the opposite. It makes things move away from each other. And not just that, this pushing seems to get stronger over time. This leads us to the idea of the Big Rip. Imagine dark energy keeps getting stronger and stronger. Right now, gravity still works fine in small areas, like our solar system. Earth still goes around the sun just fine. But what if dark energy keeps growing in power? If dark energy becomes strong enough, it could overcome gravity completely. First, galaxy clusters would break apart. These are groups of galaxies held together by gravity. Then individual galaxies themselves would start to tear apart. Stars would be flung away from each other. Next, dark energy would become so powerful that even solar systems would break apart. Planets would be torn away from their stars. Even planets themselves would not survive. Mountains would separate from the ground. Trees would be pulled from the soil. In the final moments, even people would be torn apart. The atoms in our bodies would be ripped from each other. In the last tiny fraction of a second, even the atoms themselves would break down into their smallest parts. This is why we call it the Big Rip. Everything in the universe would literally be ripped apart. From the largest galaxy to the smallest particle, nothing would stay together. The Big Rip happens if dark energy keeps growing stronger. Scientists call this a phantom energy model, where dark energy increases over time, But there is another way the universe might end suddenly. This is called vacuum decay, and it is perhaps even stranger than the Big Rip. To understand vacuum decay, think about water. Water can be liquid, solid ice, or steam. These are different states of the same thing. The universe itself might have different states too. Right now, the universe exists in what physicists call a vacuum state. But this might not be the lowest possible energy state. It might be what we call a false vacuum, like water that should have frozen but somehow stayed liquid below freezing point. The true vacuum would be like the ice, the proper lowest energy state. If our universe is in a false vacuum state, it might someday decay to the true vacuum state, just like supercooled water suddenly freezing. How would this happen? Through a process called quantum tunneling. In the quantum world of very small things, particles can sometimes do impossible things like pass through walls. Similarly, a tiny part of the universe might suddenly tunnel to the true vacuum state. If this happened, it would create a bubble of true vacuum. This bubble would spread in all directions at the speed of light. Inside this bubble, the laws of physics would be completely different. The constants and forces that make up our world would change. This bubble would grow and grow, swallowing everything in its path. We would have no warning. Since it moves at light speed, we would not see it coming. One moment we would exist, and the next moment we would be gone, transformed into something else entirely under new physical laws. Both the Big Rip and vacuum decay are sudden ends. There is no slow decline. There is only normal life until a certain point, and then rapid destruction. These endings remind us of how strange and powerful the forces of the universe truly are. To understand how the universe might end, scientists look at smaller examples. By studying dying stars and old galaxies, we learn about processes that might happen to the entire universe someday. When large stars die, they often explode as supernovas. What happens to these stars can teach us about energy, matter, and how things change when pushed to extremes. Stars fight against gravity their whole lives by burning fuel. When the fuel runs out, gravity wins. The universe faces a similar battle between expanding forces and gravity. Scientists also use computers to model different ways the universe might end. These simulations help us see what might happen over billions of years compressed into just hours or days of calculation. One famous simulation called the Millennium Simulation tracked more than 10 billion particles representing matter in the universe. It showed how galaxies form and move apart as the universe expands. By extending these simulations far into the future, scientists can see what might happen if dark energy keeps pushing things apart. Other simulations look at what would happen if dark energy weakened or changed in other ways. By testing different possibilities, scientists can see which ones match what we observe in the real universe. These computer models also help us understand vacuum decay. Scientists have simulated how a bubble of true vacuum would grow and spread. They can calculate how quickly it would move and what effects it might have. Astronomers also study light from distant galaxies to learn about the universe's fate. This light started its journey billions of years ago. By examining this ancient light, we see what the universe looked like in the past. This helps us measure how fast the universe is expanding. In the 1990s, scientists studying distant exploding stars made a shocking discovery. They found the universe was not just expanding, but expanding faster and faster. This discovery changed everything we thought we knew about the fate of the universe. Before this finding, many scientists thought gravity would eventually slow down the expansion. Perhaps the universe would even collapse back on itself in a big crunch. But the discovery of accelerating expansion showed the opposite was happening. Something was pushing the universe apart with increasing strength. Scientists have also used particle accelerators like the Large Hadron Collider to test theories about how the universe works. These massive machines smash particles together at nearly the speed of light. The collisions create conditions similar to those just after the Big Bang. These experiments help us understand the fundamental forces that control everything. They might even give us clues about dark energy and the stability of the vacuum state. Scientists have had both successes and failures in predicting cosmic evolution. For example, the discovery of the Higgs boson particle in 2012 confirmed theories about how particles get their mass. This was a major success that showed our understanding of physics is on the right track. But we have also had surprises. Dark energy itself was a huge surprise when it was discovered. No one expected to find the universe accelerating in its expansion. This shows how much we still have to learn about the cosmos. Another example comes from watching distant galaxies. Scientists expected to see them slowing down due to gravity. Instead, they found them speeding up. This observation forced us to rethink our entire model of the universe. The study of cosmic microwave background radiation has also provided case studies in how the universe evolved. This faint glow comes from all directions in space and represents the leftover heat from the Big Bang. By mapping tiny temperature differences in this radiation, scientists can learn about the shape and content of the universe. These measurements suggest our universe is flat in terms of its geometry. This flatness affects how the universe will evolve over time. It means the universe will likely keep expanding forever, rather than collapsing back on itself. Scientists also study the distribution of galaxies to learn about dark matter and dark energy. By mapping millions of galaxies, they can see how these invisible forces shape the universe. These maps show that dark energy seems to be pushing galaxies apart faster and faster, supporting the idea that a big rip might be possible someday. Each of these case studies gives us pieces of the puzzle. By combining them, scientists try to create a complete picture of how the universe began, how it is changing now, and how it might eventually end. The year 1998 marked one of the biggest turning points in the history of cosmology. Two separate teams of astronomers were studying very distant exploding stars called Type Ia supernovas. These special explosions all have about the same brightness, which makes them useful for measuring distances in space. The scientists expected to find that the expansion of the universe was slowing down. After all, gravity pulls things together. The initial push from the Big Bang should have been getting weaker as gravity tried to pull everything back together. But both teams found something completely unexpected. The supernovas were dimmer than they should have been. This meant they were farther away than expected. The only explanation was that the expansion of the universe was speeding up, not slowing down. This discovery shocked the scientific world. It meant some mysterious force was pushing everything apart, working against gravity. Scientists named this force dark energy. Dark energy completely changed our understanding of the universe's future. Before, many thought the universe would eventually stop expanding and collapse in a big crunch. Others thought it might expand forever, but gradually slow down. Dark energy showed a third possibility. The universe might expand faster and faster forever. This accelerating expansion points toward either a big freeze or a big rip. In a big freeze, everything would gradually grow so far apart that stars would burn out and the universe would grow cold and dark. In a big rip, dark energy would become so powerful that it would tear everything apart. What exactly is dark energy? Scientists still do not know for sure. The simplest explanation is that it is a property of space itself. Empty space is not nothing. It has energy. As the universe expands and creates more space, it also creates more of this energy, which pushes things apart even faster. Scientists call this the cosmological constant. Interestingly, Albert Einstein first proposed this idea in 1917. He introduced it as a mathematical fix to keep the universe from collapsing due to gravity. At that time, people thought the universe was static, neither expanding nor contracting. When Edwin Hubble discovered in the 1920s that the universe was actually expanding, Einstein called the cosmological constant his biggest blunder. He thought he had missed the chance to predict the expanding universe. But now it seems Einstein might have been right for reasons he never imagined. The cosmological constant is just one possibility for what dark energy might be. Another idea is something called quintessence. Unlike the cosmological constant, which stays the same over time, quintessence can change. It might grow stronger or weaker as the universe ages. If dark energy is quintessence and grows stronger over time, we might face a big rip. If it weakens, gravity might regain control, leading to a big crunch after all. Understanding exactly what dark energy is remains one of the biggest questions in science. Some scientists have proposed that dark energy is not a new form of energy at all. Instead, it might mean that our understanding of gravity needs to be changed. These modified gravity theories suggest that Einstein's theory of general relativity might work differently over very large distances. The biggest challenge in studying dark energy is that we cannot see it or interact with it directly. We can only observe its effects on the universe as a whole. This makes it very difficult to test different theories. Scientists use several methods to study dark energy. They continue to observe distant supernovas, mapping how the expansion rate has changed over time. They also study the cosmic microwave background radiation, the leftover glow from the Big Bang. The patterns in this radiation contain clues about dark energy. Another approach involves mapping the positions of millions of galaxies. This shows how galaxy clusters have formed and evolved under the influence of both gravity and dark energy. Projects like the Dark Energy Survey have mapped huge portions of the sky to better understand how dark energy works. The nature of dark energy will determine which end scenario is most likely for our universe. If dark energy is a cosmological constant, the universe will probably end in a big freeze. Everything will grow so far apart that no new stars will form and existing stars will burn out. The universe will become cold, dark and empty. If dark energy grows stronger over time, we might face a big rip. The increasing force would eventually tear apart galaxies, solar systems, planets, and even atoms. Everything would be pulled apart at a fundamental level. If dark energy weakens or changes to an attractive force, gravity might take over again. This could lead to a big crunch where everything collapses back together, perhaps setting the stage for a new Big Bang. There is also the possibility that dark energy itself may change over time. Recent observations hint that dark energy might not be constant. It might have been stronger or weaker in the past. If dark energy can change, the fate of the universe becomes even harder to predict. The study of dark energy remains one of the most active areas of research in physics and astronomy. New telescopes and satellites are being built specifically to study dark energy in more detail. The answers they find will help us better understand not just how the universe will end, but what it is made of at its most fundamental level. The 1998 discovery of dark energy reminds us how little we still know about the universe. Just when scientists thought they understood the basic picture, something completely unexpected changed everything. This humility in the face of new discoveries is what drives science forward. The fate of the universe depends on dark energy. Will it remain constant, grow stronger, or weaken over time? The answer will determine whether the universe ends in ice or fire, with a whimper or a bang. As we continue to study the cosmos, we come closer to understanding not just how it began, but how it might someday end. Dark energy teaches us that the universe is stranger and more mysterious than we ever imagined. The most empty parts of space hide the most powerful force in the universe. This invisible energy pushes galaxies apart against the pull of gravity. It shapes the destiny of everything that exists. Understanding dark energy is not just about predicting the end of the universe. It is about understanding the basic nature of space, time, energy and matter. It connects the very largest scales of the cosmos with the quantum behavior of the smallest particles. The story of dark energy shows how science works. An unexpected observation forces scientists to rethink their theories. New ideas are proposed and tested. Gradually our understanding improves even if complete answers remain elusive. As we look to the future, powerful new tools will help us study dark energy. The James Webb Space Telescope can look farther into space and time than ever before. The Euclid mission is mapping the positions of billions of galaxies to track the effects of dark energy. Ground-based telescopes continue to monitor supernovas and other cosmic events. The breakthrough of dark energy opened a new chapter in cosmology. It showed us that the universe is not only stranger than we imagined, but stranger than we could have imagined. The force that will determine the ultimate fate of everything we know remains mysterious, hidden in the fabric of space itself. What seems certain is that the universe will not remain as it is. Change is inevitable, driven by the inexorable force of dark energy. Whether the end comes in billions or trillions of years, whether it arrives with a big freeze, a big rip or some other cosmic finale, the universe faces a destiny shaped by forces we are only beginning to understand. The discovery of dark energy reminds us of how recently we have begun to truly understand the cosmos. Just a century ago, scientists did not know there were other galaxies beyond our own. Now we map billions of them and track their movements through space and time. Who knows what other surprises await as we continue to explore the greatest mystery of all, the universe itself. Our universe will likely die a cold death. This end is called the heat death or big freeze. Most scientists agree on this based on what we know now. The evidence points to dark energy continuing to push everything apart forever. Stars will burn out. Galaxies will grow dark. Everything will drift farther and farther from everything else. This ending happens in stages. First comes the degenerate era. This begins trillions of years from now. All stars have burned out by then. What remains are cold things like white dwarfs, neutron stars and black holes. These objects still give off some heat, but it fades over time. Planets that once orbited bright stars now float frozen in darkness. The universe during this time would look empty to our eyes. Most things are so far apart that light from one object never reaches another. Next comes the black hole era. This starts about 1 trillion years from now. By this time, even the leftover stars have faded away. Protons, which make up atoms, have decayed into smaller particles. Almost nothing is left except black holes of various sizes. These black holes give off a tiny amount of radiation called Hawking radiation. They are the last sources of energy in the universe, but they too are dying. Finally comes the dark era. Black holes eventually evaporate completely. This can take an unimaginable amount of time for large black holes. But once they are gone, nothing remains except for scattered particles. These particles are so far apart they almost never interact. The universe reaches its final state. It is cold, dark, and empty. Nothing happens anymore. Time loses its meaning. Scientists calculate the chances of different endings using mathematics and physics. They look at the rate the universe is expanding. They measure how much normal matter, dark matter and dark energy exist. Using these measurements, they can predict what will likely happen in the future. The key number is something called omega. This represents the density of the universe compared to a critical value. If omega is greater than 1, the universe has enough matter for gravity to eventually pull everything back together in a big crunch. If omega is less than 1, the universe will expand forever. Our best measurements show omega is very close to 1, but slightly less. This means the universe will almost certainly expand forever. Combined with the accelerating expansion from dark energy, this points to the heat death as the most probable end. Some scientists disagree with the heat death idea. A minority think dark energy might change over time. If dark energy gets stronger, we might face a big rip instead. Others think quantum effects might create a new universe from nothing. Some even suggest our universe might be part of a cycle of death and rebirth. We still have much to learn about dark energy. We do not fully understand what it is or how it works. Future discoveries could change our predictions, but based on what we know now, the heat death seems most likely. This end will not happen for an incredibly long time. The universe will remain somewhat like it is now for trillions of years. Stars like our sun will shine for billions more years. Even after our sun dies, other smaller stars will shine for trillions of years more. Life and civilization could continue for an almost unimaginable time before facing the final darkness. Could intelligent beings change the fate of the universe? Might future advanced civilizations find ways to prevent cosmic death? Scientists have thought about these questions. The answers involve extreme physics and the limits of what might be possible. The laws of physics set boundaries on what anyone could do. No civilization, no matter how advanced, can create energy from nothing. The law of entropy says disorder always increases in a closed system. These rules limit how much even the most advanced beings could change cosmic destiny. But within these limits, future civilizations might try some amazing things. One idea involves black holes. Black holes concentrate matter and energy. Some physicists have suggested advanced beings might create and manage black holes as energy sources. This concept is called black hole farming. A civilization might feed matter into black holes and then harvest the Hawking radiation they emit. This radiation would be the last available energy in a dying universe. Black holes with the mass of stars can last for unimaginable periods. A black hole with the mass of our sun would take about 10 circumflex 67 years to evaporate. That is far longer than the current age of the universe. Another theoretical possibility is creating new universes. Some physics theories suggest it might be possible to create baby universes in laboratory conditions. These would form separate spaces with their own laws of physics. They would expand into their own independent realities. The energy requirements for creating new universes would be enormous. It might require focusing the energy of an entire star. The technology would be far beyond anything we can currently imagine. But the physics might not completely forbid it. Some scientists have also considered the idea of escaping to other universes. If our universe is part of a larger multiverse, perhaps advanced civilizations could find ways to travel or send information between universes. This remains purely theoretical. We have no evidence that other universes exist or that travel between them would be possible. Information preservation presents another approach. As the universe dies, advanced beings might focus on preserving knowledge and consciousness. They might convert themselves into forms that use extremely little energy. They could enter periods of hibernation, waking only rarely as the available energy diminishes. How can we tell what interventions might really be possible versus pure science fiction? Scientists look at what the laws of physics allow. Some ideas require new physics that might not be correct. Others would need nearly infinite energy or other impossible resources. For example, reversing entropy throughout the entire universe seems impossible based on known physics. Creating wormholes to escape the universe might also be impossible. But some ideas, like using black holes as long-term energy sources, do not obviously violate physical laws. The distinction comes down to energy requirements and the fundamental limits of physics. Can the intervention work within known conservation laws? Does it respect the speed of light limit? Does it account for quantum mechanical limits? If the answer to these questions is yes, the intervention might be physically possible, even if far beyond our current abilities. Most importantly, any cosmic intervention would face the challenge of scale. Our observable universe spans 93 billion light-years. Even the most advanced civilization would find it nearly impossible to affect such vastness. They might preserve their local region for longer, but changing the fate of the entire cosmos seems beyond reach even for beings millions of years more advanced than us. Life would face growing challenges as the universe ages. Living things need energy. In the far future, energy becomes scarce, stars burn out, temperatures drop toward absolute zero. How might life adapt to these harsh conditions? Biological life as we know it could not survive these changes. Our bodies need warmth and chemical energy. We rely on our sun and its light. When stars die, planets freeze. Traditional biology becomes impossible, but intelligence might find new forms. Some scientists think consciousness could transfer to artificial substrates. These might use far less energy than biological bodies. Freeman Dyson, a famous physicist, wrote about this possibility. He suggested that intelligence might slow down its thinking as energy becomes scarce. Dyson proposed that beings might think slower and slower as the universe ages. Each thought would take longer, but use less energy. In this way, subjective experience could continue even as objective time stretches to enormous spans. What feels like a normal thought process to these beings might take years or centuries of actual time. Life in this era would focus entirely on energy efficiency. Every calculation, every thought would be optimized to use minimal energy. Beings might enter long periods of hibernation between brief moments of activity. They might merge individual consciousnesses into collective minds to share limited resources. As stars burn out, life would need to use other energy sources. Brown dwarfs, which are failed stars, last longer than normal stars. After they fade, rotational energy of neutron stars might be harvested. Black holes would be the final energy source through their slow Hawking radiation. The challenges become more extreme as time passes. During the black hole era, intelligent beings would need to operate at incredibly cold temperatures. Traditional computing as we know it would be impossible. Quantum effects would dominate. Computation might need to use entirely different principles than what we understand today. Eventually, even black holes evaporate. The final era leaves only scattered particles in an ever-expanding void. Could life continue then? Some theoretical physicists think certain kinds of computation might still be possible, but it would be nothing like life as we understand it. The universe places an ultimate limit on computation and thought. Entropy cannot be reversed across the entire cosmos. Eventually, the available energy becomes too diffuse to support any form of organized complexity. At this point, life and consciousness must end. What makes this limit so fundamental is information processing requires energy. Every calculation erases previous information states, which produces heat. In a cold, expanding universe, this heat is eventually lost forever. When no more energy gradients exist to exploit, no more thinking can occur. Freeman Dyson and other scientists who have studied this question differ on how long life might persist. Dyson was optimistic, suggesting intelligent beings might find ways to extend subjective experience almost indefinitely by thinking ever more slowly. Others point out that quantum mechanics may set more strict limits. What connects cosmic endings to consciousness is energy. Both life and the active universe depend on energy flowing from concentrated sources to diffuse states. When this flow ends, both end. The story of life and the story of the cosmos share this common thread. Knowing the universe will end changes how we think about existence. Different potential endings raise different philosophical questions. A heat death suggests a gradual fading away. A big rip or vacuum decay suggests a more dramatic end. Each scenario shapes how we might find meaning in a finite cosmos. Time flows in one direction. Physicists call this time's arrow. Entropy always increases. Eggs break but never unbreak. Coffee cools but never spontaneously heats up. These everyday observations connect to the universe's fate. The same principle that makes your hot coffee grow cold will eventually make the entire universe cold and lifeless. This irreversibility raises deep questions. If everything eventually dissipates into random motion, what ultimate purpose can anything serve? Religious and philosophical traditions have wrestled with these questions long before modern cosmology. They offer different perspectives. Many Western religions describe an end to the physical world but continuation of spiritual existence. Eastern traditions often view reality as cyclical, with endings leading to new beginnings. Modern secular philosophies seek meaning in what exists now, rather than in eternal continuation. The heat death specifically challenges our sense of purpose. If the universe ends in cold emptiness, does anything we do truly matter in the end? Philosophers have several responses to this challenge. Some argue that meaning exists in the present, not in eternal consequences. A beautiful sunset has value even though it lasts only minutes. Human experiences have worth regardless of whether they echo for eternity. Others find meaning in the patterns and connections we create during cosmic history, even if those patterns eventually fade. Learning about cosmic endings affects us psychologically. People react differently to this knowledge. Some find it depressing. Everything we build will eventually be erased. Others find it liberating. The vastness of time gives perspective on daily troubles. Still others feel awe at being part of such a grand cosmic story, even if that story has an ending. Science itself offers a philosophical perspective on cosmic endings. The universe operates according to patterns we can discover and understand. This suggests a kind of meaning through comprehension. By understanding the universe's life cycle, we participate in something larger than ourselves. We become the universe understanding itself, even if for a brief moment in cosmic time. The philosopher Albert Camus wrote about what he called the absurd. This is the conflict between our desire for meaning and purpose and an apparently indifferent universe. Camus suggested we can create meaning by acknowledging this tension and choosing to live meaningfully despite it. Modern cosmology makes Camus' point concrete. We exist in a universe with a beginning and an end, and must find meaning within those boundaries. Finding meaning in a finite cosmos ultimately becomes a personal journey. Science tells us the universe will end. It cannot tell us how to feel about that fact. Each person must integrate this knowledge into their own understanding of purpose and value. Both science and philosophy help us navigate this profound question. We now understand that the universe had a beginning and will have an end. Between these points stretches a vast but finite story. We know the universe began about 13.8 billion years ago in the Big Bang. It will likely end in heat death trillions upon trillions of years from now. We live in the middle of this story, during what astronomers call the stelliferous era, when stars light the darkness. This knowledge places human existence in context. Our species has existed for only about 300,000 years. Human civilization is younger still. Written history covers merely 5,000 years. These time periods seem long to us, but they're incredibly brief compared to cosmic time frames. An individual human life lasts about 80 years. Compare this to the 13.8 billion year age of the universe. If the entire cosmic history were compressed into a single Earth year, human civilization would appear only in the last few seconds of December 31st. Your entire life would be an imperceptible fraction of the final second. This perspective can change how we view our lives. Our daily concerns often consume our attention. Will I get that job? What will people think of me? These questions feel enormously important. Yet when viewed from cosmic time, they shrink to insignificance. This can be both humbling and freeing. The cosmic perspective reveals connections between humans and the universe. The atoms in our bodies formed in stars that died billions of years ago. When we look at the night sky, we see our origins. We are made of star stuff, as the astronomer Carl Sagan famously said. We are the universe becoming conscious of itself. This knowledge should inform our values and priorities. If human civilization represents a brief luminous moment in cosmic history, we should treasure this moment. We should work to extend it as long as possible. We should preserve what we have learned and build upon it. Knowledge itself becomes precious. Each discovery adds to our understanding of the cosmos. Each artistic creation captures something of the human experience within this vast story. Preserving and expanding knowledge becomes an almost sacred duty when we realize how rare and fragile intelligent life may be in the universe. We face many short-term challenges today. Climate change, nuclear weapons, and emerging technologies pose risks to civilization. The cosmic perspective reminds us what is at stake. If human civilization ends prematurely, we lose the opportunity to fulfill our potential in the cosmic story. We lose the chance to learn, to explore, perhaps even to seed consciousness elsewhere before our sun eventually dies. The knowledge that the universe will end gives extra weight to these concerns. If consciousness is rare in the cosmos, and if all naturally occurring consciousness must eventually end, then each moment of awareness becomes infinitely precious. Each civilization that develops becomes a brief candle in an otherwise dark cosmos. Protecting and nurturing our particular candle takes on profound importance. Living with cosmic perspective means holding two seemingly contradictory ideas in mind simultaneously. In cosmic terms, we are insignificant. Our lives are inconceivably brief, yet in another sense we matter enormously. We are the universe experiencing itself. We are matter arranged in such a way that it can contemplate its own existence and future. This is, as far as we know, extraordinarily rare. The end of everything reminds us of our common bond. All humans share the same cosmic story. We face the same ultimate fate. Our differences, while real and important on human scales, fade when viewed against the backdrop of cosmic time. We are fellow travellers on a journey with a beginning and an end. Perhaps most importantly, cosmic perspective offers a kind of immortality through understanding. Though each of us will die, and though the universe itself will someday end, knowledge transcends individual existence. By learning about cosmic history and future, we extend ourselves beyond our brief lives. We become part of something larger. We participate in the universe's attempt to understand itself before time runs out. The facts of cosmic mortality need not lead to despair. Instead, they can inspire wonder and gratitude. We exist during the bright middle act of the cosmic drama when stars shine and life is possible. We have developed the ability to discover our place in this story. Few things could be more remarkable than this accomplishment. The universe began in fire and will likely end in ice. Between these points exists the only moment when beings like us can live and think and love. By understanding our cosmic context, we can appreciate how precious this moment truly is. We can find meaning not despite cosmic endings, but because of them. The transience of existence gives it value. In the cosmic perspective, we find both our insignificance and our worth. We are tiny fragments of the universe that have, against incredible odds, gained the ability to comprehend the whole. We exist for the briefest moment of cosmic time, yet in that moment we touch something eternal through understanding. We become not just witnesses to the cosmic story, but conscious participants in it. This is our place in the history of everything. We live in the bright middle chapter of a book that has a beginning and an end. By studying that book, we transcend our brief appearance in its pages. We glimpse the entire story from its fiery opening to its cold conclusion. And in doing so, we fulfill what may be the universe's deepest purpose. we make the cosmos conscious of its own magnificent finiteness.